In this video, we're going to look at indeterminate forms and L'Hopital's rule. So recall that the forms 0 over 0, infinity over infinity, 0 times infinity, 0 to the infinity power, infinity to the 0 power, 0 to the 0 power, 1 to the infinity power, and infinity minus infinity are called indeterminate forms because they don't give enough information to guarantee that a limit exists or what the value would be if it does exist. Sometimes to find a limit resulting in an indeterminate form, we can use algebra to manipulate the function. So for something like this, I've got the limit as x approaches 0 of e to the 2x minus 1 divided by e to the x minus 1. So you know that if you were to try to plug the 0 directly in here, you would get 1 minus 1 and 1 minus 1, which would give you 0 over 0, which would be this indeterminate form. So we can't do that because you can't divide by 0. So we have to have some way to make this indeterminate form become a form that we can evaluate. So the way that I would handle this one without using any special rules is what we've done in the past. I would factor this. So e to the 2x minus 1 factors to be e to the x minus 1 times e to the x plus 1. So I would rewrite this as the limit as x approaches 0 of e to the x minus 1 times e to the x plus 1 all over e to the x minus 1. And then I'd cancel those. And I now have the limit as x approaches 0 of e to the x plus 1, which is something I can plug directly into. So I drop my limit notation, and I get 1 plus 1, or 2. So that's one way that you can do it, by factoring and canceling where appropriate. You may have also multiplied something by a conjugate to evaluate a limit that's an indeterminate form. But there are some indeterminate forms that can't be manipulated in this way. So that's where L'Hopital's rule comes in. So for something like this, the limit as x approaches 0 of e to the x minus 1 over x, you would end up getting 1 minus 1, which is 0, over 0. And we can't cancel or use any obvious algebra to find the limit. So the only thing we would be left with would be plugging in numbers on either side of 0 and making a chart, or using the rule that's coming up next. L'Hopital's rule says let f and g be functions that are differentiable on an open interval from a to b containing c, except possibly at c itself, and we assume that g prime of x is not 0 for all x in the interval from a to b, except possibly at c itself. So if the limit of f of x divided by g of x as x approaches c produces the indeterminate form 0 over 0, then the limit as x approaches c of f of x over g of x is equal to the limit as x approaches c of f prime of x over g prime of x, provided the limit on the right exists or is infinite. This result also applies when the limit of f of x over g of x as x approaches c produces any of the indeterminate forms infinity over infinity, negative infinity over infinity, infinity over negative infinity, or negative infinity over negative infinity. One thing that's important to note is that this is not the quotient rule, the derivative with respect to x of f prime over, of f of x over g of x. This is actually finding f prime of x divided by g prime of x. A lot of you tried to do that for the quotient rule, but that wasn't correct. You needed that gf prime minus fg prime over g squared for the quotient rule for the derivative. This can also be applied to one-sided limits as well as general limits. So using this rule, let's evaluate that limit we looked at a second ago. The limit as x approaches 0 of e to the x minus 1 over x. So we verified that this is a 0 and this is a 0 if you just try to plug the numbers in. So what I'm going to do then is I'm going to apply L'Hopital's rule, and just to remind myself of what I'm doing, I like to put a nice L and an R on top of it, just to show that I'm using L'Hopital's rule. So the derivative of the numerator here, the derivative of e to the x is e to the x. The derivative of negative 1 is 0. And the derivative of x is 1. So I now have the limit as x approaches 0 of e to the x over 1, which is something I can directly substitute into. So I get e to the 0, which is 1. One of the cool things about L'Hopital's rule is that it can be used on any limit that is going to end up being an indeterminate form. So one like this, if I were to plug in a 3, I would get I would get 9 minus 18 plus 9, which is 0 over 0. So you have to do something. And the old way we would have approached this would be to factor and cancel. The limit as x approaches 3 of this factors to be x minus 3 squared over x minus 3, and then you cancel. And now we can plug in to get 3 minus 3 or 0. And that's fine, but most of you hate to factor. So if that's you, you can use L'Hopital's rule instead of working it the old way. And we're just going to take the derivative of the top, which will be 2x minus 6, and the derivative of the bottom, which is 1. And now that's something we can plug in, because instead of having a 0 on the bottom, we have a 1 on the bottom. So this would be 2 times 3 minus 6, which is 6 minus 6, or 0. So you can see you get the same answer either way you do it. Here we have one where if you plug in a 0, you would get sine of 0, which is 0, sine of 0, which is 0. So L'Hopital's rule applies here. And I'm just going to make a little note that I'm using L'Hopital's rule. The derivative of sine of 5x is going to be 5 cosine of 5x. And the derivative of sine of 3x is going to be 3 cosine of 3x. And now when I plug in, cosine of 0 is a 1. So this gives me 5 cosine of 0 over 3 cosine of 0, which gives me 5 times 1 over 3 times 1, or 5/3. So we can do that without having to use any special algebra tricks. We're just using the derivative. Here's another one. If I plug in 1, I would get 0 over 1 minus 1, which is 0. So we're going to use L'Hopital's rule. So we'll have, let's see, the derivative of natural log of x cubed is 3x squared over x cubed. That's u prime over u. The denominator gives me 2x. So I'm going to clean this one up a little bit. And I'll have 3x squared over x cubed times 1 over 2x when I keep change flip. So this x will cancel, just leave an x here. So we'll have that. So I've got limit as x approaches 1 of 3 over 2x squared. And now this is something I can plug into because I'm plugging in a 1. So I would have 3 over 2 times 1 squared, or 3/2. We said earlier that you can also use L'Hopital's rule for the indeterminate form infinity over infinity. So you do want to verify, hey, if I take the limit as the top approaches infinity and the limit as the bottom approaches infinity, that I do actually get something approaching infinity over infinity. And in this case, as x approaches infinity, natural log of x would approach infinity, and obviously the denominator would as well. So this is an indeterminate form, and we're going to use L'Hopital's rule. So natural log of x will become 1 over x, and x will become 1 when we take the derivatives. So I'm taking the limit as x approaches infinity of 1 over x. So this is now a number, it's a constant over infinity, and we know that if the numerator stays constant and the denominator approaches infinity, then the whole limit approaches 0. And that's just kind of a rule in general. Anytime you have a constant number over something approaching infinity, it's going to go to 0. Anytime you have a constant number over something approaching 0, it would be either plus or minus infinity, depending on what's going on there. Let's look at the next one. We've got x over e to the 3x. Again, something that's going to infinity and something that's going to infinity. So we can use L'Hopital's rule. So the derivative of x is 1, and the derivative of e to the 3x is 3e to the 3x. So now we have a number over something that's going to infinity, so that will be 0. With this one, we'd have infinity cubed, infinity plus 3. So using L'Hopital's rule, we would have 3x squared over 1. And as x approaches infinity, now this is going to approach positive infinity. So that would be the answer there. You may encounter some situations where finding finding the limit cannot happen just from one application of L'Hopital's rule, and you still get an indeterminate form. And in that case, you can just apply the rule twice. So with this one, I've got the limit as x approaches negative infinity of x squared minus 4 over e to the negative x. So the numerator here, when you square a really large negative number, you get a really large positive number, and subtracting 4 from it doesn't make that much of a difference. So this goes to infinity. Here you would have e to the negative infinity, basically, so this is also going to approach infinity. So we'll use L'Hopital's rule and get the limit as x approaches negative infinity of 2x divided by negative e to the negative x. So with this one, we end up with negative infinity, and in the denominator, we're going to have negative infinity as well. So I'm going to use L'Hopital's rule again. So I'll have 2 over positive e to the negative x, and this is now a fixed constant number over something that's going to approach infinity. So this is going to be 0. One thing that I do want to point out is that this particular limit right here is not evaluated by L'Hopital's rule. A number divided by something approaching infinity is not an indeterminate form. That gives you 0. It's only something that is infinity over infinity, or 0 over 0. Let's look at another one. I've got the limit as x approaches infinity of the natural log of x to the 4th divided by x cubed. So this one is infinity, this one is infinity, so we can use L'Hopital's rule. So I will have, let's see, 4x cubed over x to the 4th for my numerator. The derivative of x cubed is 3x squared. So I'll clean that up just a little bit. And I'll get 4x cubed over x to the 4th times 1 over 3x squared. So this one, we'll do some canceling, and I'm going to have, let's see, 4 over 3x cubed. Now this is very important. Again, we only use L'Hopital's rule this one time. This one is not L'Hopital's rule. Okay, you cannot do this limit by L'Hopital's rule. You just have to observe that this is a number over something approaching infinity, which is going to give you a 0.